Continuing on physical chemistry, chapter 12, we're in section 12 now. In this section, we're going to talk about three-component systems, also known as ternary systems. These are interesting in chemistry and geology. So, the degrees of freedom is going to be equal to 3, because we have 3 components, minus the number of phases, plus 2, or just 5 minus the number of phases. So if the number of phases is 1, then we get F is equal to 5 minus 1 is equal to 4. So the degrees of freedom would be something like temperature, pressure, the mole fraction of substance A, and the mole fraction of substance B. Now, of course, to graph that, we need a 4-dimensional graph. So on a more practical matter, what we do is keep temperature and pressure constant. Then we can show all 3 mole fractions on a 2-dimensional graph. So what we do is we make an equilateral triangle. So you notice how we have substance A, substance B, substance C. So if you're at this point, you have pure A. If you have this point, you have pure B. If at this point, you have pure B. C. So the line here. Okay, so we're at a point here, right? D. Anywhere inside. We draw a line straight over here, straight over here, straight over here. This means 90-degree angle, 90-degree angle, 90-degree angle. So all 3 of these lines are perpendicular. This line is perpendicular to this line is perpendicular to this line is perpendicular to this. So the length of this line will give you the mole fraction of substance A. The length of this line will give you the mole fraction of substance B. The mole fraction of this line will give you the mole fraction of substance A. The reason we do that, we set it so this line, see, where are we? DE plus DF plus DG, that's going to be the H. That's a math formula. That's going to be H. So if we set the length to 1, what I said is true of the mole fractions. If you don't set the overall size to 1, then it won't come out right. So like I said, if you set H equal 1, then of course your mole fraction A plus your mole fraction B, mole fraction C is going to add up to 1, like it has to, because you have 3 components. So like I said, the mole fraction of A, that's going to be the length of this segment DE. The mole fraction of B, that's going to be equal to the length of this segment DF. And then the mole fraction of C, that's going to be equal to the length of this segment DG. So this works with real substances. Let's say we have acetone, water, and ether. Now this is interesting because if you have acetone and water, they're completely miscible. If you have acetone and ether, they're completely miscible. But the water and ether, they're only they're partially miscible. They're miscible in a small amount here, but not in here. So anywhere out here, you have only 1 liquid phase. We're talking about liquids, of course. And then in here, you'll have 2 phases. And the tie lines are not horizontal. It's a bit more complicated. So this is assuming that we have 30 degrees and pressure is 1 atmosphere. Because like I said, we have to keep those 2 constant anyway, or we'd have a 4-dimensional diagram. Now, like I said, water and acetone, they mix well. They're highly soluble. Ether and the acetone, they mix well. They're highly soluble. But the water and the ether, they don't mix as well. They're partially soluble. Now, K is called the isothermal critical point. Was that on the diagram? Okay, so right here, you've got a point K where it's a certain temperature, but you got a critical point. Now, the tie lines in this example are diagonal. Like I said, on the regular phase diagrams, they're all horizontal. But you still use the lever rule. You get the number of moles, the substance F. Wait a minute, substance F. Okay, so here we are. Yeah, that's written kind of funny. I'll have to check on that. So the number of moles at F is equal to length Fg, and that's going to be equal to GH times the number of moles of H. Okay, that is all for section 12, and that's also the end of chapter 12.